All right, subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is section 13.3, which deals with liquids and solids. Now before we get into the details of the notes, here's a couple of objectives you should be able to meet by the end of this video. Objective number 1, apply the kinetic molecular theory to the behavior of liquids and solids. Objective number 2, relate properties such as viscosity, surface tension, and capillary action to intermolecular forces. And objective number 3, compare the structures and properties of different types of solids. So let's go ahead, we'll start out here with liquids, and we're going to start out with some basic properties here. So number 1, liquid particles are in continuous motion as predicted by that kinetic molecular theory. The other thing to keep in mind is that liquid particles are very, very closely packed together. And the reason that these liquid particles are very closely together is because of the forces of attraction between liquid particles. So remember, if we're talking about forces between two particles, we're talking about intermolecular forces. Now, what happens here, because liquid particles are closely packed, the range of motion is going to be limited in liquids. Now, even though the range of motion is limited, liquid particles can still slide past one another, and we'll talk about that here in just a few moments. But the last point I want to make related here to this closely packedness of the liquid particles is this: they cannot expand to fill its container. Now, more simply put here, this last point I made here, we just call that as having a fixed volume. So liquids have fixed volumes. Now, the other major point that I want to make on this section of notes is this: liquid molecules do not have fixed positions in their particles. And since they don't have a fixed position, it's going to allow liquid particles to flow past one another. And as a result, the liquids are going to take the shape of their container. So even though liquids have a fixed volume, they do not have a fixed shape. All right, so we can continue moving on here with some more details of liquids. And we start out here by talking about the density of liquids. Well, liquids are going to have a much higher density than gases. And this is because liquid particles are much closer together. Now, as the density of a liquid increases, that is caused specifically by an increase or the larger number of intermolecular forces that are holding liquid particles together. Now, let's put this in terms of an example, and that is liquid versus gaseous water. The liquid water, the liquid H2O, is about 1,250 times more dense than water vapor, the gaseous form. Again, that says liquid water is 1,250 times greater or more dense than water vapor. All right, so what we can also talk about here is how a liquid can be compressed, or the compressibility of a liquid. And liquids can be compressed because some space is going to exist between the particles in our liquid state of matter. Now, I want to put this in perspective here and talk about our liquid particles. So let's say we have a beaker, and it contains some liquid particles here that I'm going to represent with a blue pen. And so let's say our liquid particles here are contained in this portion of the container. Well, number one, if you compare this to pictures of gases, which we discussed in section 1, these liquid particles here that I'm drawing are much, much closer together
But what I want you to notice is that there's still some space, and obviously I'm exaggerating the space here and the size of the particles, obviously, but there still is some space, some empty space that allows the gas to be, or excuse me, the liquid to be compressed. So just remember, there is a lot less space than we have with a gas. And remember, this is due to the tightly packed particles that are contained in a liquid. Now, to be able to compress a liquid, we're going to have to apply large amounts of pressure to be able to just compress the liquid by a few percent, or just by a little bit. Now, these two properties, the density of liquid and the compressibility, are some things that engineers really look at when they're talking about some different liquids and some different structural things that they need to do and how liquids affect that. So it does have some engineering applications of our liquids. Okay, so now we can move on to another property here of liquids. And that property is known as fluidity. Now, fluidity is just defined as the ability to flow. Now, liquids are much less fluid than gases. And this is because liquids are going to flow much slower than gases at the same temperature. And if you look at the very details here, the reasons that liquids are going to flow much slower is because the intermolecular attractions are much greater in liquids and interfere with the liquid's ability to flow. Now, if we put these things into an example, it may be easier to see what happens with the fluidity of a liquid. So let's say, for example, you have a gas leak versus a water leak in your home. With a gas leak, the gas can easily diffuse or move throughout the house if you open something like a window or a door open. And this is often the remedy that you'll see fire departments use if there's a carbon monoxide leak and they shut the gas off where the source is coming from, and then they open up the window and wait for that gas to get out of that area, because eventually it will, and it'll come back down to a safe level. Now, on the other hand, if we have a water leak in a house, that water is going to remain in that area until it reaches the level of a window. So essentially the water is almost stuck in place. So that water is going to remain in that one area, in this case the house, until it is going to exceed the volume of the container. So this is why if somebody has water damage in their house, they usually have to call a service. Surf Pro is usually in our area, but they come and they'll remove that water. And that's why people have water damage. There's a lot more than something like a gas leak. And that's all the ability for it to flow. Now we can move on to yet another property of our liquids, and that is known as the viscosity. Now, the viscosity is defined as a measure of the resistance of a liquid to flow. Now, what we have to remember is that particles in a liquid are close enough for the attractive forces, those intermolecular forces, to slow their movement as they flow past one another. Now, the viscosity of a liquid is determined by three things. The first is the intermolecular forces of the liquid. The stronger those attractive forces and intermolecular forces, the higher the viscosity. Now, the other thing that we have to consider here is the shape and size of the liquid particles. The larger the liquid particle, the greater the viscosity. Now, to go along here with the shape and size, if we have a long chain liquid molecules, those long chains are going to have higher viscosity. And then our final factor here that affects the viscosity is the temperature of the liquid. The higher the temperature of the liquid, the lower the viscosity is of the liquid. And so the reason that as we increase the temperature of the liquid, we're going to reduce the viscosity, the reason for that is the kinetic energy contained within the liquid is going to increase. And if we have more kinetic energy contained within the liquid, what happens here is that it makes overcoming the intermolecular forces easier. And as that becomes easier, then the liquid can flow more easy. All right, so now we can move on to what we call surface tension. So surface tension is defined as the energy required to increase the surface area of a liquid by a given amount. And so what it's doing is actually measuring the inward pull by the interior particles of a liquid. So with a liquid, we have to remember that particles can be attracted to any other particles around them. That means particles above them, below them, and to either side, a liquid particle can be attracted to. And so surface tension is a result of the unequal intermolecular forces that exist within the liquid. And so let's draw a picture here, and then we'll explain the details of the picture. So let's say, again, we have our beaker of water. That's a good liquid to use here. And so what happens here, we're going to focus in on this big blue dot. But remember, that big blue dot is going to be surrounded by other water particles, okay? And so what happens here is this, and I'm going to exaggerate this with the arrows, but the forces of attraction are going to be unequal. So what happens here, and I'm trying to emphasize this, that there are larger forces of attraction pulling down and inward here, and this is going to cause that surface tension. So let me mark that here as larger inward attractions or larger attractions below the water particle of interest. So there it is. The water particle is having a larger, greater force pulling down on this particle, which results in that surface tension. Now, specifically, the details of what's happening here is that at the surface of the liquid, there is no attraction from above to balance the attraction from below. So as a result of this business here, what happens here is that the net attraction pulling down on a particle at the surface experiences, again, that net downward pull. So with this, the surface of a liquid tends to have the smallest possible area. Now, increasing the surface area is going to require particles from the interior to move to the surface, which requires energy. Again, this says increasing the surface area requires interior particles to move to the surface, which causes or has to have energy involved in this. All right, so to go along with surface tension, we have a lot of different liquids, and so this means that we're going to have a lot of different strengths. So the strength of a surface tension is going to depend on the attraction between particles. And that statement can be made with this: the greater the attraction between the particles, the stronger the surface tension. And a good example of this is liquid water. Liquid water is going to have high surface tension because it has multiple attractions between the particles. And remember, these great attractions are from the multiple hydrogen bonds. And then the other thing that we must contend here with liquid water is that the surface area of water molecule are spheres. And remember, that shape here of a sphere impacts the attractive forces that can be all around that of water. So that makes it significant. Not only do you have the strongest intermolecular force of a hydrogen bond, but you can have 360 coverage all the way around one water molecule to make that sphere of a circle. Very cool thing here, if you actually take just a drop of water on a penny, you'll see it bubble up. And that bubbling is that sphere that I'm talking about here in notes. Now, our other topic that we need to talk about with surface tension is what we call surfactants. And these are defined as compounds that lower the surface tension of water. Now, the surfactants here, I can show you the impact with a little experiment. So I'm going to pause the video. I'm going to set something up here to show you a little demonstration of what we are just talking about. Okay, so I have my setup. I just have a beaker of tap water here, and I have this little push pin. And what I'm going to do here is I'm going to float the pin. And so the way I float the pin is by doing this. I have just a little paper towel, and I'm going to set the pin on the paper towel and slowly, and I went too fast here, so I'm going to have to grab another paper towel. I'll pause the video real quick. Okay, so let's try that. Attempt 2. Again, I just have the small little push pin. I'm going to set it onto a paper towel and gently place this into our beaker. Okay, so now what I'm going to do here with a paper clip is just kind of push down the sides of our paper towel and float the pin. So again, all I'm going to do here is I'm just going to slowly take a paper clip here that I folded out, and I'm going to soak this paper towel so that a way it will fall to the bottom. And I got to do this really slowly, or else the pin itself will fall to the bottom with the paper towel. Okay, so there we go. So the paper towel is at the bottom, and you can see here that the pin is actually floating. So again, the pin is floating on the water. I'm going to adjust the camera so you can see maybe a little bit of that, but the pin itself is floating on the water. Oh, there's a good shot right there, okay? So we've actually floated this metal pin because of the surface tension of water. Now what I have in this other beaker here is soapy water. So what I'm going to do is I'm just going to take one drop of this soapy water and I'm going to put it on the side, and the soapy water, I should mention, acts as a surfactant here. So I'm just going to put a little bit of that soapy water, and you can see that the pin moves to the other side. And as I just put one drop of that in the water, what happens is this. The surface tension gets broken, and you can see the pin gets moved. And again, if I put just one drop of this soapy water, it's going to affect the pin. Now, as I put some more soapy water into this, the surface tension will be broken. So again, as I put this in here, again, the surface tension is broken, and I did not touch the pin with the water. What happened is the surfactant, the actual liquid water, broke the surface tension, and that pin that was floating, hopefully you heard that hit the bottom of the beaker, that allowed that to happen. So I'm going to clean up here, pause the video, and then get back to notes and explain specifically what happened here in our example. Okay, so the reason that that floating pin sunk to the bottom is that when we put the surfactants here, which were soaps and detergent, it decreases the surface tension of water by disrupting the hydrogen bonds between water molecules. And again, our example here is soaps and detergents. So as we added the soap there, the soapy water, the surface tension of the water was disrupted by affecting the hydrogen bonds between water molecules. And so when these hydrogen bonds are broken, the water spreads out, or the surface tension decreases. So all of this explains why that push pin that we had fell to the bottom when I put those couple drops of soapy water in there. Okay, so now we can move on to our final portion, our final topics here of liquids, and that is cohesion and adhesion. Okay, so cohesion is defined as the force of attraction between identical molecules. And an example of this would be the hydrogen bonds between water molecules. Now, adhesion is defined as the force of attraction between molecules that are different. An example of this would be why water is attracted to the side of a glass beaker. Now, cohesion and adhesion can help explain why we have a meniscus form in something like a graduated cylinder. So remember, if we have a graduated cylinder here, and remember, graduated cylinders are typically pretty narrow tubes here, and I'll draw some markings on here to represent that we have our graduated cylinder. And if I fill this up with water and I say, hey, go measure the amount of liquid. Remember, you should always measure from the meniscus there. And remember, the meniscus itself is going to form this curved line. So the meniscus here is that curved line. Now, the way cohesion and adhesion play a role in this is as follows. The adhesive forces between water molecules and the silicon dioxide in glass are greater than the cohesive forces between those water molecules. Now, because the adhesive forces between water and that silicon dioxide is greater than those cohesive forces, this is going to cause water to rise along the inner walls of our graduated cylinder and create that meniscus. Okay, so our last thing that we can talk about here with liquids, or the last thing we are going to talk about, is what we have known as capillary action. Now, capillary action here is going to occur when the cylinder that contains a liquid is extremely narrow. And so when the cylinder is really narrow, a thin film of water will be drawn upward in the narrow tube. And this capillary action is one simple explanation of how water is absorbed in a paper towel. Okay, so now we can transition to solids. So we learned a lot about liquids, and we can transition to that knowledge of solids. And so we start out here with solids, and we're going to start with some basic properties. Okay, so we have to keep in mind that we're explaining the properties of solid through the kinetic molecular theory, and we have to think about the following. Okay, so the first thing that we have to be aware of here is that a mole of solid particles has much more energy than that of a mole of a liquid particles at the same temperature. So again, that is a mole of solid particles has as much kinetic energy as a mole of liquid particles at the same temperature. Now what that means, the important part here is that if this is true, kinetic energy is energy in motion, that means particles in a solid must be in constant motion. Now, solids have the strongest attractive forces between particles. Now, these strong attractive forces are going to limit the motion of the particles to vibrations around fixed locations. Now, we should also note here that the force in these solids are greater than that of liquids. Now, since solids have such great attractive forces, what we also have to talk about is their order. Now, solids are going to have more order than liquids because the motion of particles are limited. Now, because of this great order that solids have, they are not classified as fluid. Okay, so now we can move on and talk about the density of solids. So generally, solids are more dense than liquids. And now this is because the particles in a solid are more closely packed than those in a liquid. And again, another general statement here, but for most compounds, the solid form of matter will sink when placed in that same liquid form of matter. Now, the changes in pressure will not change the volume of a solid because those particles in a solid are so closely packed together. And to put it simply here, solids will not compress. Now, there's one major exception to this density of solid trend, and that is water. In water, the ice form, which is the solid form or the solid form of water, will float in the liquid form. This is because liquid water is more dense than solid water. Now, what happens here is that solid water, or ice, is less closely packed together than liquid water. Now, this causes more space to be in molecules of ice. And as a result, it causes the ice to be less dense than liquid water. Again, that says ice is less dense than water. Now, a major thing for this, I'm going to put it in red, the major thing here, why this all happens, is a big result from hydrogen bonding. Okay, so this hydrogen bonding, the strength of hydrogen bonding in water causes all of these things to happen. If hydrogen bonding wasn't there, most likely this stuff wouldn't happen and ice would not float in that liquid water. Now, we can move on here to our next topic of solids, and that is of crystalline solids. So, crystalline solids are defined as a solid whose atoms, ions, or molecules are arranged in an orderly, geometric, 3D structure. Now, these crystals in the crystalline solids are the individual pieces of these components. Now, crystalline solids are composed of unit cells. Now, unit cells are defined as the smallest arrangement of a connected points that can be repeated in 3 directions to form the lattice. Now, unit cells can be arranged in different ways. So if we look at an example here, our cubic unit cell can be arranged 3 different ways. Now, what we can also talk about here back on our notes is the different shapes of crystals. Now, these different shapes, maybe you saw it from the chart, but they are located on this particular chart we'll talk about here in a second, but they're determined by the unit cell from which the lattice is built. And there's 7 different categories of these crystal shapes that exist. And of these 7 shapes, the shapes are going to differ. So again, I already started writing on our page here where we talked about the different unit cells. But if we look at this here, obviously one type of crystalline solid shape can be arranged different ways. And that's what this form shows. This is just a cubic, which is one of 7 different ways. Now what this chart here shows is the 7 different crystalline shapes. And I'm not going to get into the details here. You have this chart to reference, but you can see that of these different crystals, the 3D shape or the three-dimensional shape is a little bit different for each category, and the solids can be classified in each of these areas. Now we can talk about these different classes of crystalline solids. Okay, so for our crystalline solids here, they can be classified based on the types of particles they contain. And there's 5 different classes of crystalline solids. One of the 5 solids are atomic solids. Another class is molecular solids. An additional class is covalent network solids. The 4th class is an ionic solid. And our 5th class is a metallic solid. Now we'll go through each of these classes of solids, but what I've provided for you in notes is this chart that summarizes each of those 5 categories that I just listed. Now it's nice, it tells you, hey, what kind of unit particle does it have? What are some of the characteristics and some of these examples? So we'll start out here and we'll start talking about atomic solids. Now, atomic solids are only composed of noble gases. Now, remember a couple things. Noble gases are found in group 18 of the periodic table. And these things here, the reason that we have atomic solids is that noble gases are able to form atomic solids because of their weak dispersion forces between the atoms. And for our noble gases, that is the only type of intermolecular force. Now, if we shift gears here and we go to our molecular solids, we can see how they differ. Now, molecular solids are solids that are held together by dispersion forces, dipole-dipole forces, or hydrogen bonds. Now, normally they are composed from small molecular compounds. Now, most molecular solids are not solids at room temperature because of their small size. And this small size of molecular compounds results in smaller intermolecular forces between each of the molecules. Now, I should have started this up here, and I should have started it with if they are composed from small molecular compounds, these are their properties. Now, down here, if they are composed of large molecular compounds, they're going to have the properties that are going to be listed below. And so one of the properties here is that if they're large molecular compounds, they're typically going to be solids at room temperature. And that's because their large size results in greater intermolecular forces between molecules. Now, an example of this is sugar. Now, all molecular solids are poor conductors of heat and electricity. Now, our next class of solids that we need to talk about are covalent network solids. Now, these are solids that form as a result of multiple covalent bonds. Now, examples of these things are examples of elements that form covalent network solids include things like carbon and silicon. Now, an example of a covalent network solid is quartz. So our other type here, our next type of covalent solid is an ionic solid. And an ionic solid is a solid that the structure and shape is going to depend on the type of ions and the ratio of ions in a compound. And remember that ionic substances are composed of oppositely charged particles. Now, the network of attractions is going to extend throughout the ionic crystal, and that provides them some unique properties. Now, properties of ionic solids include high melting points, high hardness, being strong but brittle, and they can shatter easy due to repulsions between ions of like charges. Now, this causes the cations and anions to be shifted from their fixed position when an ionic solid is shattered. Now, our fourth type of solid here is a metallic solid. And a metallic solid is going to form in compounds that have metallic bonds. And now remember, the strength of metallic bond is going to vary among different metals. And so because the strength varies, the properties of metallic solids vary. An example of this is tin, which melts at 232 degrees Celsius. But a metal with metallic solids such as nickel is going to melt at 1,455 degrees Celsius. Now, there are some shared properties between all substances that have metallic solids. One of which is that they are ductile or can be drawn into wires. And they are good conductors of heat and electricity. Okay, so now we can transition here to our last type of solid. And that last type of solid is known as an amorphous solid. And an amorphous solid is defined as a solid in which the particles are not arranged in a regular repeating pattern. Now, an amorphous solid often forms when a molten material cools too quickly to allow enough time for crystals to form. And now, examples of amorphous solid include things like glass, rubber, and many plastics. Now, glass may be thought to have some sort of structure, and they're using devices with neutrons in them to try to determine if there actually is a structure in glass. But right now, they can't really find a definite pattern in that glass or silicon dioxide. All right, so this concludes this episode here of Science with Surbeck. We learned a lot about liquids and solids. I put a lot of information into these notes. I hope you have enjoyed this episode, and if you haven't already, make sure you subscribe.